Hi, my name is Amir Azadi. I'm in machine learning team at Wolfram Research, and I will be talking about unsupervised learning function in Wolfram language.
Hello everyone, I'm Amir Azadi, and today I'll be talking about unsupervised learning functions and some new updates that will be coming in 12.1 and some review of new features that we had in 12. What is unsupervised learning? Broadly speaking, unsupervised learning tries to learn unknown patterns from unlabeled data, which can unlock various tasks. It is in contrast to classify and predict where you have labeled data. So unsupervised learning tasks that I will be talking about today, I will start from clustering, then go on to dimension reduction, and then the next step would be learn distribution, which will unlock a lot of other tasks that will follow, like find anomalies and synthesize missing values. So let's start with just clustering, one of the classic examples of unsupervised learning. And the goal is simply partitioning data into clusters of similar elements, and the measure is based on some distances or dissimilarity functions. Two main functions that we'll be using today is find clusters, that you can input the data directly and get the clustering result as an output, as a default output, and the other one is cluster classify. So these functions work on a variety of data types, including images, numerical and nominal, dates and times. So let's look at the first one, find clusters let's try it on a list of numerical values. So you can see that it returns a sublist of clusters. You can also, as a second argument, specify how many clusters you want. And it will tell you that there are two clusters of similar elements. The other function is a cluster classifier, which returns a classifier function, cluster classifier function. You can train it on a set of data, and then you can use it for your test data, which returns the index of the clusters associated with each of your examples. As I told you, it works on a variety of data like images. Let's look at like train classifier, cluster classifier on images, asking for 3 clusters, and you can gather those by their cluster index. The main thing that we can have is the clustering methods. You can specify what method to use. There are around 10 methods that has been implemented, and a few of them will be updated in 12.1. And different clustering methods often lead to different partitioning of your data. And the method's performance in general depends on various things like the shapes of the clusters, the sizes, density, and the level of noise in your data. And in general, there is no good universal metric to compare the performances of different clustering methods. For instance, looking at this complex structure, we as humans who would like to find patterns in everything, yes, we might find different patterns, but different clustering methods might result in different clusters. All the methods in 12.1s are documented in details about the details of the algorithms, and users can go and look at different methods and choose the one that they think that it's best possible for their data. But let's look at one of the applications and one of the new updates on one of the widely used clustering methods, DBS Scan, which this method finds cluster as a connected component of highly dense regions. You can go and look at the details of it in the documentation pages, and accompanied with some toy data sets and the performance of that. But one important thing is that the DBS Scan can also find outliers. And the outliers would be labeled as the missing anomalies. labels. And you can just drop them if you want with a sub option of the method drop animals values. It will be in 12.1. You can also see that clusters of anisotropic Gaussian structure. You can also see the gray dots or the outliers picked by DBS Scan method. So let's change gear and go to the other task of the unsupervised learning, dimensional reduction, which is often used for visualizing higher dimensional data in lower dimensional space, and it is good for feature discovery and so on. Again, two main functions that we will be using today is dimension reduction and dimension reduce, which works for, again, a variety of data types like images, textual and numerical and nominal data. Again, you can, here I have a simple three-dimensional vector. Dimension reduce directly give you the reduced data in the target dimension. You can also specify the dimension of the target to be, for example, 1. The other function related to dimensional reduction analysis is dimension reduction itself, which you can give it a set of training data, and it will return a dimension reducer function that then you can use that function to reduce new data. And depending on the method that you use, you can have two types of mapping from higher dimension to a lower dimension. It can be linear mapping or nonlinear mapping. By default, the automatic methods would do a linear mapping of your data. And linear mapping are all somehow different variations of principal component analysis and lower matrix factorization that tries to find the target space spanned by direction of maximum variance of the data. So those are your principal components that linear methods or automatic method would use. So let's look at one of the example using Fisher iris dataset, which is a dataset of different species of flowers given its physical characteristics like sepal and petal length. So it's a 4-dimensional data set. And we can just perform a dimensional reduction on that, and you can see that plotting that in the reduced dimension, you kind of see that the same species cluster together in this lower dimensional space. But this linear mapping doesn't always work, especially if your data lives on a higher dimensional manifold, which is complex and it's non-linear. A very simple toy data set that shows you this non-linearity is this Swiss roll data sets. So as if you just use a linear method on that, it would just squish all of your data projected to just one plane. So you just lose all the information about the global topology of your manifold that the data lives in. There are a few methods in non-linear methods that you can use. One of them is like LLE, locally linearly embedding, which tries to preserve the local neighborhood relationships of the points. And it kind of, as you can see, it can unroll the data in lower dimensional space without using the information about the local and also the global geometry of your data. You can also, there are examples of dimensional reduction that you can use methods like a variational autoencoder that you can use that depends on under the hood. It uses neural networks and so on, and you can use it. It's very good to use it on images and so on. I won't go into the detail as there are not much time on that, and I'm gonna switch gear to the next section which is learning a distribution of the data, the statistical distribution of the data that underlies data. This data can be anything, can be just numerical variables, it could be numerical vectors in any dimensions, it can be nominal, mix of those images, and so on. So what is it good to know the distribution of the data? So you can do a lot of things, and it's one of the central applications of unsupervised learning, actually. You can by having trained distribution, you can generate a new sample, you can synthesize new samples. You can query probabilities of new samples. You can find outliers and anomalous examples. You can filling missing values, you can denoise and decorrupt your data. So there's a variety of tasks that can be unlocked by knowing the distribution. So the main function is just learn distribution in Wolfram language introduced in 12, and there would be a detailed talk by Etienne Bernard at 3:30 today, which will tell you all about the details and all the knobs of learn distribution. But I would need to go through quickly how it works. You just give the learn distribution your data, and it would return a learned distribution. Based on that, you can ask for a PDF of a new example. You can also get random variate, work on the learned distribution, and get synthesize new examples. Unlike the other methods where the automatic setting for method selection does not exist, since there is no universal metric for clustering and for dimension reduction to compare the performances. Here we have for learned distribution, we have a very clear metric, which is the cross entropy, the log probability of your examples, and you can simply compare all the methods performances with just this one metric. And what under the hood learn distribution does is it would go try different methods and subset of data, and it will pick the one that with the smallest loss. In general, learning a distribution from unlabeled data, it's more harder than classification tasks. And there will be some more methods in the future. And the problem is some methods wouldn't be able to correctly find the probability density functions like GANs that are very good in synthesizing new images, but you cannot really get the probabilities. So let's look at one of the example again on Fisher-Iris data sets. I only pick two of the features in the data. Since it's a four-dimensional data, I just make it a two-dimensional based on petal and sepal length of the flowers. And you can learn distribution on that, and then you can get like random varied new examples. And you can look at the contours of probabilities overlaid on top of it with the data points. As you can see, places where you have a lot of data, so you have 2 peaks of your distribution. As you go further away from the peaks, you would kind of have no mass, probability mass density. For instance, if I ask for a PDF of like somewhere here, a test example here, you get a pretty low PDF. So now you can say, it might give you a hint that some examples could be anomalies. But let's talk more about anomalous examples. So in general, a naive definition of anomalies is examples that are kind of different from the others. Here we focus on the problem when you have anomalies are rare. If they're not rare, you can use just classify, and if you have labeled data. But it is only when you have unlabeled data and anomalies are rare. These are the assumption, and the other assumption is that the distribution, you have a known distribution. Given the known distribution, you can find out of distribution examples, anomalies, in another word, with a function called rarer probabilities, which what it does is it computes the total probability. It computes the total probability for distribution to generate samples with PDF lower than the example that you're querying. For example, if I have a learning distribution here and I ask for a rarer probability of 3 and 100, since 3, you would say, yes, it is not very rare. It's just 0.5 to have samples generated by this distribution. And then 100, which is far away, as you can see from these training sets, that you would get a very tiny, rarer probability for that. So this is our metric to identify anomalous examples. So we will consider examples, anomalies, when the rarer probability is below an acceptance threshold, a given acceptance threshold. The default acceptance threshold is 10 to the minus 3, 1 in 1,000 examples. So we use this mechanism to design find anomalies function, which you can give it a learn distribution as a first argument and examples that you want to find the anomalous ones in the second one, and it can give you the anomalous examples, and you can also change the acceptance threshold and so on. But you can also directly use find anomalies as here on the data. You might think that how about like if you don't have the learn distribution on non-anomalous data? So this is like a chicken and egg problem. You want a distribution on non-anomalous data to find anomalies, but on the other hand, you don't know where the anomalies are. So we have also a scheme for that. We do a cross-validation, and we learn the distribution on the examples with the highest rare probability, and we train on that, and we find anomalies on the rest. And we do it a few times if you don't have a learn distribution. In general, you can go to the documentation, but there are a lot of few properties that you can query from find anomalies. Like by default, it returns the anomalous examples, find anomalies for you, and you can ask for the position of the anomalies, rarer probabilities of them, and so on. Let's look at one of the applications for finding anomalies for images. Here I have a CFAR 10 from the resource data that are images. As you know, it's a standard benchmark for various type of images like planes, dogs, cats, and everything. And I added a few just random noise to the data set. So you can just learn the distribution on those images, and you can ask for anomalous examples given that learn distribution. You can see it makes mistakes for sure, but you can change the acceptance threshold to see and explore different outputs. Here I also added some noise to few examples of the CFAR 10, and you can get the noisy ones out as anomalies. So I'll change gear again, and another task unlocked by learn distribution is synthesizing missing values. So often you have data that are missing. Often there are corruption in your images, and you would like to replace it with better values. So there are there's just only one main function, synthesize missing value, introduced in 12. You can directly give it your examples, or you can, again, as a first argument, give the learn distribution, and the second argument, the examples that you would like the missing value to be imputed. So very similar to find anomalies. We learn a distribution, and how it works is you can easily condition the distribution if you have, like, say you have x-axis missing on this two-dimensional vector that I just learned distribution on. You just condition on the known values, which is you condition your distribution on the 4.5 on a y value, and you draw a sample for x on that conditional distribution. And by default, it would just give you the missing and replace it with a new sample. And actually, what you can have a different, in general, the formalism works like this, that we have an expected maximization algorithm underlies, which iterates between training the distribution, imputing the missing values, and just train the distribution again on that imputed, and just do it again and again to get the best missing value synthesized for you. There are different methods that you can use. You can draw just random samples from the condition distributions by asking for the evaluation strategy to be random sample, or you can ask for the mode of the distribution with mode finding sub-option. And the learning method would just ask for what type of method for learn distribution to use. So again, let's look at Fisher-Iris data sets and learn distribution on that. So as you can see, we have the contours of the probability density function. And say I have a point, x is like around here, but you don't know what is y. So the y can be like anything on this axis. So I just synthesize missing values here, and you see that it gives me 1.8, which is around the mode, the peak of one of the mode of the distribution. It's a bimodal distribution here. Let's look at like around 1,000 imputed missing values. And as you can see, I'm drawing random sample from the distribution for the missing values on the condition distribution, which is conditions on a known x values. And you see that it goes around this mode, and sometimes it goes around this mode. You can look at the histogram of these, and you see it is following kind of a two-modal distribution here. And if you ask for a mode, it would just give you the one which is closest to the mode of your distribution. So by default, synthesize missing value when you input your data. Synthesize missing value, treat missing and indeterminate as missing, and it will replace them. But you can change that behavior. There's the option missing value pattern. For example, you can say treat 4 as missing here, and replace and synthesize for that missing pattern. Or you can just have other functions, say like less than 3 should be treated as missing. Let's look at one application here, which is like in Painter. If you have like a cropped image and you want to paint that image. So I do it on a MNEST data set, and just a subset of that to be fast. Again, I learn a distribution. I just also specify what method to use, so the automation. If you don't do that, the automation would find the best methods based on the cross entropy. And one thing is you can also ask for information about the learn distribution, and you can see the learning curve based on the training example, and the loss, the entropy, and different algorithms that it tries, and so on. Back to the synthesized missing value, given that learn distribution, I have like 2 kind of cropped images, and I say treat 0.5 as missing. So, and it would and use the mode finding, like draw a mode from the condition distribution, and it will just fill in the missing values for us. So you can think of, we were thinking about adding other methods as GANs, a talk gave by Jerome earlier today, would be a good candidate for synthesizing missing values for images. And for right now, learn distribution and derivatives functions like find anomalies and synthesize missing does not work on sequences like text, audio, and in the future we're thinking about adding those. And thank you very much for your attention. That was all I have. I would be happy to take any questions.